All right, so we have about 20 minutes for a 45-minute lecture, so I have to skip a few parts. So because Stefan took a little longer, unfortunately we're a bit on a tight schedule today because of the excursion, so I'll just try to see if I can fit it in as little time as possible so you still have time for lunch. All right, so I'm going to talk about object recognition with dynamic neural fields. And so first maybe a little bit of motivation. You've now seen the scene representation, but and the short version is in the scene representation. So we always use just the color information of the objects and the inputs we have. So we have camera input, as Stefan has probably shown you this image up here. But he doesn't really extract any information about the objects. It's just like, this is a red object, the other one is blue, yellow, and so on. And so you don't really have any information about these objects. If you interact with a robot, rather than just having the scene representation, which demonstrates some cognitive principles, you actually want to have knowledge about the objects. You want to maybe know that you can use a hammer for hammering stuff, or the way you grasp hammers, like something that Stefan maybe also showed in the end. And so just a short motivation about why it's difficult to actually recognize objects. So if, let's say, you know just this one image here of this object, and if I then show you other images of this object, these can look drastically different. Even that's not even the case in the images I show here, but if you take, for example, this image, the complete background has changed. If you take this image here, the lighting is completely different. So if you want to do just a pixel by pixel comparison between the images, you won't really recognize that these are the same objects. And it gets much worse if you have 3D transformations, or like rotations in the third dimension, and translations even maybe. Because, for example, this pose here looks radically different from this one, and if you didn't know this beforehand, you probably wouldn't recognize this if I only showed you this version of that. Okay. And so, yeah, the real problem is that we have a three-dimensional object. We cast a two-dimensional image in where if you use, for example, a camera, and that kind of totally changes the object. All right, a common solution to that, an usual approach is just to take invariant feature detectors. So I'm going to skip this a little bit because otherwise it will take too long. We can also detect the object pose, which is what we will do in the system I will show today. So in general, we define the object pose more or less as detecting the center of the object. The system I will present today will sort of detect this in the image plane rather than actually in the three-dimensional space. And so this can be helpful for various things, for example, for the grasping, as Stefan has probably shown a video of. And yeah, okay. So and the real important part here today will be sort of a DFT implementation of the Arathon approach. Has anyone ever heard of that before? Has anyone heard of David Arathon's work? No, probably not. There's probably a good reason for that. And you can maybe gauge it from these images. So you can see that he's kind of working in military research. So his stuff is published. He wrote a book on that. And that's a good book you can read if you want. He also published 2 or 3 papers on that, but then he kind of vanished, probably because, well, he's in military research, so he probably can't publish everything he does. And well, yeah, you can kind of see that here. And that's kind of unfortunate because this approach he has is really nice. This is just an example from one of his papers, which you can read if you want to know more. He has the three-dimensional model of the tank, and what he does is an iterative process due to competition and so on. I will not explain this in too much detail because our approach is actually quite similar and is just a neural dynamic implementation of that. He starts looking at the whole image, and then over some iterations here, he sort of converges. You can see here much of the input is actually faded out. And he ends up having just matched this one tank, and so in the end he will have pose parameters saying how to rotate and shift this three-dimensional model to actually overlay in the best way possible with this one final image then. All right, so we're talking about pose estimation and object recognition, so we have to define 2 things for DFT. How do we actually represent our pose parameters, and how do we actually represent our label or recognition decisions? So representing the pose is kind of straightforward, I think. So you should have heard about these 2- and 1-dimensional fields in the lectures this morning by Sebastian Schneegans. So if you want to represent pose, this can, for example, be an orientation, an angle. Since we're working in the image plane, this angle is, of course, just 1-dimensional, so we can use a 1-dimensional field like this over here. And then if you have a peak, for example, at this position, this tells you that the angle that the object has is essentially whatever angle this corresponds to, which is maybe, I don't know, 110 degrees or something like that. And for the shift, which is 2-dimensional in the image plane, of course, you can then use a 2-dimensional field which has just an X and Y position, which tells you where the object is actually located. Okay. And for the labels, it's a little more complicated. We actually have discrete labels if we want to have a label recognition, of course, because we have one object and we have a label. This is object, I don't know, the phone, the glass, maybe something like that, right? And so in DFT, there's no natural discreteness, right? This is a continuous feature space. And rather than, and that's sort of kind of a little conflict, but actually you can solve this kind of nicely, and I don't know if Gregor talked about this in his lectures. So if you have a pre-shape, which has small bumps, so you've learned maybe through various presentations that the inputs always come at 2 certain positions, then actually if you have a peak that forms slightly off that position, you will see a drift of that peak towards these categorical positions, and from that sort of categories emerge. But that's just a short version of that. So in the end, you end up with just fixed locations where there can actually be peaks forming, or where all peaks will be moved towards or drawn towards. And so from that, we can sort of see that as the concept of a label field. And we simplify that to having just sort of discrete positions where we have label activation. So we disregard all the metric space because in these instances it doesn't really bring us so much, and we just take the activation at the places where we actually have the labels. So this is just simplified down to just having one point of activation, or one, in a sense, one neuron or one node, really much more, because you don't really have a neuron that stands for one thing, that represents how much you perceive one specific object. Anyway, this label space is also one that has no intrinsic metric, of course, or at least none that's trivial anyway. So you cannot say the label for a glass of water is that and that far apart from, I don't know, an eraser or a cell phone or something, because it's kind of difficult to embed these, right? So that's kind of the problem of categorization. Anyway, let's try to actually get to the real object recognition system, and that's what I would think I would spend most of the time on now. So I will explain this with an example. So we will restrict here to one-dimensional shifts. So we have 2-dimensional images, and we will shift them only along the horizontal dimension to just understand the principle. You can do more transformations, and I will explain that later on, but for now let's just keep it simple. So in the vein of keeping it simple, let's say we have the input we see up here. So we have the sunscreen tube, and we have an input image here that we want to actually have, and we want to estimate how much this is shifted towards that. Kind of seems like a trivial task if you see it in isolation like this, of course, because you can just easily shift this with things around, so you could probably solve that quite quickly, I think. But actually, we will in the end do much more and do more in parallel with this, so it won't be that easy now. But for now, if we want to actually do that, and if we want to do that with our system, we start out with a shift estimate, and this is kind of the first thing that we can get from the Arathon approach. So because we don't represent the pose over we just have one pose value, so we don't say our pose estimate is 4.5 in the x direction, for example, but rather we have for each possible pose estimate, we have a sort of likelihood how much it is shifted. We can, in the beginning, say we don't really know anything, so we say that all poses are equally possible. Right? And this is what we get from the field representation in this case. So this isn't quite really a field, but it's kind of behaving similarly, right? So if you have questions, just interrupt me. Right? So, okay. So anyway, if we have that, and this is again the idea that we have more or less taken from Arathon, we can do a weighted superposition. So we can say we can shift the image that we know or that we want to look for. We can shift that to each position in the input space. And we can weigh that by the current shift estimate. Because they're all equally likely, you just get a shifted version of this at every position in the input, right? So this is just a sketch, so it should really be smeared out across everything and so on. And if you have that, you can actually match that to the input, right? Disregard that that's shifted, that's just a bug in the presentation software. If you have that, you can easily check this against each other, and then for each shift location, you can estimate how much that fits the current input. So really, you could be done now. You could say this one is the version that matches best with this one. But again, because we have a recurrent process later on, we actually don't want this to instantly converge to this, because later on we won't know so well how our actual object looks like or what our object is. So we take this matching value, we use it as an update. So we see that all the ones over here match a little bit or very well with the actual input. These ones over here don't match very well at all or match really nothing. So the ones that match here, this one and this one here, they give a high value, so the probability of them being our pose or the activation of the pose is still high, whereas the other ones start decaying. right? And so we can keep iterating that. So we can now update our weighted superposition. Now it doesn't look so trivial anymore. So we now have actually something that looks a bit different. So this one actually faded now because the likelihood or the probability of that is gone down. And so if you measure that again, you again get a very low value, whereas these stay. And if we continue to do that iteratively, in the end, ideally at least, we will converge to the correct pose. So everything else has gone to 0. Then we have one peak in here, so sort of like the neural field peak, which tells us the shift of that object is here. Okay? So that's how we actually do the transformations, at least the shift transformations. That's the first part of this. And so we haven't really talked about how we actually recognize an object yet, right? So really the normal case is that we know a set of objects, for example, these 4 up here, and we have some input image, and we want to find out what object we actually see in this input image. And the pose estimation of that is just a sort of a bonus, which makes it easier for us to match this to the stored views. All right, so we use similar ideas to the actual process of matching the shift here. So here we have sort of one probability of seeing this object or one activation of this object for each object, right? And we start out again saying that we don't really know anything, we don't really know what's in the input, and we want to estimate what the input is. So we again have activation values here, so we say the prongs here are very likely and everything else is equally likely. All right, so we could form a weighted superposition again, right, like this. So we can again take each value here, weigh the actual object image, the object view we have, and sort of sum all of that together. But that doesn't really help us for matching, right? So we can't take this, match this in some way with that image and find out how likely each object is again. But we will, for a later process, need these ones, so we will just keep doing these. The actual matching then happens by taking the input image, which ideally is already aligned with these object views we've stored in memory, and comparing that to each object we have, so each object view we know. And if you do that, then again, the process is quite similar to what we did with the shifting. So for example, if we match this to the prongs, these won't match very well, but maybe a little bit due to the color here.
So the matching is pixel by pixel?
Yeah, actually, yes. I will explain the actual matching. So this is more or less a sketch, so I don't actually give any details here. So you could do that in any way you want. Essentially, you have one image here, and you have stored images, and you can match those in any way you like. So we do that with a correlation, actually, which is pixel by pixel, right? But you can do that in other ways as well. Also, our patterns in the end aren't color images, but rather extracted things. I'll talk about that a little bit later. Okay, but anyway, yes, you can match these pixel by pixel or in any method you like, anything that gives you a similarity between this image and what you've stored in your view. And if you do that, then you can update again the activation values of each node. And you can continue iterating that in a similar manner to how we did it in the shift. So in the end, the superposition will sort of start converging towards the actual object. So in the end, you have maybe something that looks like just a superposition between the toothpaste tube, the green one, and the sunscreen tube, because they're quite similar in some senses. And the rest is just being faded out, yeah. And if you converge, hopefully, you will also get only the correct object being active, and you will have, in the end, an output from the top down, essentially, that matches the input as good as it gets, right? So now we've sort of had two paths here. We have, for one, we've estimated the shift, and in the other direction, we've sort of estimated the labels. But if you, for each of one, for estimating the shift, you had to know what the object in the input was already. For estimating the label, right, back here, we actually assumed that this is already aligned perfectly with memory views, right? So to actually do object recognition, now we have to combine both of these parts, right? So this is the one where we matched the object. This is the one where we shifted it around. And so kind of the question is, we have, for one, we have the representation of the shift, and we have the representation of the labels, and we sort of want to get to the correct version in the end. So how do we combine these? Well, hopefully it's already obvious, but probably not. Anyway, so we start out. So this is really a recurrent process, so everything kind of happens at the same time. So what order I go through these is kind of arbitrary, but so I like to start thinking about how we actually just do the weighted superpositions. So we take our current pose estimate, and we take our current label estimate and we calculate the weighted superpositions again. So we take this here, shift it all around, so this is going kind of the other way around now. And we also take all our label informations that we currently have, generate the weighted superposition. And if we have that, we can also take this top-down pattern and also shift it around everywhere. So this is just the superposition of all the views we know, because currently all the weights are the same. And yeah, so then we are kind of set up for updating our actual pose estimate. And so this is where the recurrency actually starts being positive for us, right? So we started off knowing nothing. Now we have sort of these things here which we can match to the input. So we can already use, for example, this here to determine the shift. So we won't get a perfect shift estimate, but you can already see quite well that this in any shift comparison. So if you maybe do a correlation again or a cross correlation as we do, you will see that this kind of matches here quite well. So there's objects in these places, and here there's nothing, so these will return quite low match values, right? And so the same for the labels. So if you match this image here to all of the labels you know, you won't really get a precise answer yet, because this is just a smeared out version of the input, but you can already see maybe that this fits kind of well with the sunscreen tube, and maybe a little bit with the toothpaste tube, but not very well with the prongs here. And so you can keep updating this. And if you keep updating this, because you already have a hint of what's actually going on, or of what you're actually seeing, because, for example, the sunscreen tube has a kind of competitive advantage because it matches better, then actually the rest gets sort of faded out again. And so this kind of starts converging towards the actual thing that we have. So if you look at the superposition now, which is, again, it's just a sketch, but it starts looking much more like what we actually see in the input. And because it starts looking much more like what we see in the input, these shifted versions also start looking much more like that. And so it's much easier to actually determine the pose and match that in the end. And if we keep doing that, at some point this will kind of, at least hopefully, converge to the correct version. So meaning that we will have only one pose active, one shift active here, and only one label will remain that's actually active here. So we've recognized what the object is. Oops. And that means we can perfectly estimate its shift under ideal conditions again, and we can also perfectly match it towards the objects. So we will just, over time, sort of fade out all the information that we know is not correct. And because it's a recurrent process, we can start from this assumption in the beginning that we don't know anything, and that we can just fade everything out. And Arathon has actually shown that this converges mathematically. So if you're interested in that, you can also look that up in his book. And it's kind of nice. But I will not go into detail about that. So some details. So far this has just been a sketch. Maybe first, are there any questions about that already? No? Was it clear? Hopefully. Okay. Anyway, the full system that we use actually uses different feature channels and also some slightly modified versions of this. So far I've shown three channel images, color images, but really what we do is we do edge extraction, and then we use sort of localized histograms, which are sort of taking around a certain position, and then extract the edge orientations and also a color histogram from that. And we also use a shape channel, which is just extracted sort of algorithmically, more or less. Yeah, okay. How can we realize the transformations? So I've described this verbally for now. If you write down an equation for that, it actually becomes kind of obvious what that is, I think. So essentially what we do is we shift a pattern we want to sort of shift, or of which we want to generate the shifted superposition. We first shift that, for example, to the very left, and then we take the current shift estimate value that corresponds by that, multiply the shifted version, and add it to the final image, right? And we do that for all the possible shift values, okay? And the mathematical version of that is just that we form the sum over the image shifted by some shift value Si, and weighted by the current shift estimate, which here I've called PSI. And really, of course, I mean, this is the discrete version of that, which is, of course, also implemented on any computer system. But if you really look at that, it's really, because the shift estimate is going to end up being a neural field, this is also a continuous version, really. So the shift is represented of a continuous version. So if you write it down properly, you actually end up with the equation for convolution, right? So if you've seen convolution, that should look familiar. There is a question how neurally realistic that is. and I'm running out of time, so I have to speed up a little bit. So the interesting part here is that, for example, our pattern, so this is just simplified as a slice through this two-dimensional pattern, but you can think of this as a two-dimensional pattern, everything still holds. The pattern is represented in neural activation, so for example, this could be an edge image or a slice from an edge image where you see you have an edge here and an edge there, and you want to sort of generate the shift of that or the convolution of that, and you want to shift that by something that's also stored on an activation pattern, which is shown up here in the shift version, right? Now the problem is that if you want to have neurons doing that, essentially you have to go to each position, multiply 2 activations of neurons, and then write that into an output. And so the problem is that for that you need sort of multiplicative synapses. I don't think I have time to go into too much detail, but so multiplicative synapses, they kind of are debated, but there are convolution networks which use them. And in addition to that, so this is kind of a little bit of a weird way of drawing the convolution, right? But you may have seen something similar in Sebastian Schneegans' lecture where he actually showed the transformation fields. And so you can sort of also do it with that. Okay. Interesting is maybe also how we actually match patterns, because it was also asked before. So again, here a simplified version where we just look at one-dimensional patterns. And so the trick we use is essentially that we do correlation with normalized patterns. Normalized meaning that we've taken the mean value away from them. So we've shifted them to be centered around their mean value, so they're mean-free essentially. And so they're also normalized in their height. So if you take 2 patterns, for example, the one up here and this one down here, and if you want to match those, and these ones look quite similar, if you multiply them point by point, right, you multiply this place with the one up there, you get something that's positive because both of them are positive. Down here, both of them are negative, so you get something positive again, right? Minus times minus is plus, of course. If you do that across the board, these 2 patterns which match, they will have positive or 0 values everywhere here. And if you sum that up, you get a positive value, which then tells you that the match is kind of positive or good. If you have patterns that don't match or that match perfectly badly in this case, then you have exactly the opposite case. You have a negative value here and a positive up there, which yields a negative value down here. And the same is true again for also across the whole dimension. And if you sum that up, you get a negative value, and so that kind of is a mismatch value. All right, and so then you can use this kind of correlation to kind of find how well that works. All right, I will skip more stuff again. So of course, now we've only talked about one-dimensional shift so far. And of course, if we want to estimate the pose of an object in the image, we really want to also estimate rotation and maybe even scale for that. The way we do that is actually we use the same principle again. So we use, again, shift estimates. And we just transform the image into log polar space. So if you look at a square in log polar space, for example, here, and if you shift it along the distance dimension of the log polar space, of course, it will get scaled, right? So if we shift along the distance dimension, the square just becomes bigger. So if you do it for all the 4 points of the square, just transforms. The same goes for the angle dimension, of course. Naturally, if you shift along the angle dimension, you will just get a rotation. And so if you do that, you can sort of cascade multiple transformations. And this is shown here. So for example, if you start with an input image, then first you estimate the shift. This is now a 2-dimensional shift estimate, of course. The 1-dimensional was just a simplification. You can, in the end, then here log polar space, which allows you to estimate the 1-dimensional scale and rotation here. Actually, it's the other way around. And in the end, then you can estimate the labels. Of course, this kind of diminishes or sort of makes it more complex to find the optimal solution or to find the optimal pose, and gives you more local minima and so on. So kind of it works a little worse than, but it still works. Okay. So, all right. So I've kind of hinted at that before, so we'll use these localized histograms. I will skip just very briefly. So that means that we have a sort of small location in which we extract a weighted histogram. So the further we are away from the center, the less the entries get weighted. So we, for example, if we take the color, if it's far away from the receptive field center of one of the histograms, it's not weighted very much. And if it's close to the center, you can maybe see that better here, it actually gets weighted quite a lot. So for example, you can see the blue color here, which is relatively far away from the center, I can't quite reach, has a very low influence here. Okay. Maybe interesting now is to look at some results. So these are published results. You will find these in the Farbe-Schönert 2009 paper. So we've evaluated the system in the COIL database on the first 30 objects. The COIL database, those of you who have done vision before have probably heard of that. It's a data set where sort of, I think altogether 100 objects have been photographed from views like these. So they have been rotated on a turntable, and then they've been cut out and so on. So that's also, so first we see these objects from many different sides. So we have the problem again that I've kind of skimmed over at the beginning, that objects can look very differently from their different sides. But with just one training view, so just using one view of the object, we can already achieve 85% recognition rates. So if we then try to address this problem of the different views from different directions, we can already get up to 94%. So we've addressed that by just having 4 training views. So looking from the front, from the side, from the back, and from the other side. Okay, and I really have to hurry up now. We've also devised our own training data set, which you can sort of have a glimpse at here. So that's of 30 common household objects like screwdrivers. Well, one could argue those are not so common, but still they're common in our robotics lab. And these are placed at different positions. So for example, here we have a screwdriver, and here you can see all the 9 positions that we've put it in. So the thing about this data set is that you can immediately see that we've sort of taken it so that the transformations are not really 3-dimensional, they're more 2-dimensional, or they're almost 2-dimensional for, if you look at these images, right? We've also got 3 cutout regions, so we only restrict the input to these areas and to where the poses are in to recognize them. Anyway, if we do that, we can get up to 90% correct recognition. All right, just a brief video, and hopefully that all works. Oh yeah, nice. Aspect ratio is a bit off, but I think we'll live. So this is actually a video taken from the live system, from the newest implementation of that. So this is also done in CEDAR, by the way. So you have the input image up here, and you have the pose representations here. So we have 2 layers for these pose representations, which is a sort of something we need because we use dynamic neural fields, because we sort of initially want to estimate all the poses that are possible, which is a detection decision. So we want to know what can be, or what are possible poses and what aren't possible poses. But of course, in the end, we want to end up with just one decision. So we want to know what, or we want to have a decision what the exact shift, rotation, and scale, well, scale isn't actually in here, of the object is, and we don't want multiple answers for that. But of course, to have the error-thon approach, we first have to have candidates. And that's what we solve by having 2 layers. So for example, we have the rotation layer 1 and the rotation layer 2 here. So the first layer is the one that actually does the detection, so it's relatively fast. And so this will first give multiple candidate poses. The second layer will be a lot slower, and this will be best viewed in the labels, I think, which will then just make a selection decision. All right, down here, I think it's best to just see what that is. Also, I've made a mistake here. I have plotted the shift layer 2 twice, so it will look the same. All right, so you can see now. So we've started recognizing. So in the first layers here for the rotation, for example, you see 3 candidate solutions, sort of, right? We have one possible orientation here, one here, one here. And in the label layer, you can also see sort of that there are emerging, I think, 4 candidates. So 2 here, 1 here, 1 here. The correct one, I think, is label 3. We'll see. It will converge to the correct one in the end. I've made sure of that. And down here, you can't really see anything yet, but it will happen soon. All right? You see everything. So the first label layer goes towards, kind of closer towards the actual threshold for detection. And so you can see now here, a lot has been sort of faded out. And this is sort of kind of the nice thing. If we actually have the pose of the object, we can take our current estimate of the shapes and just overlay this with the input and then just fade out the input. This doesn't fit very well yet because we don't have any correct recognition yet or any good recognition yet, but it will feel better in a while. So you can sort of guess or sort of get a glimpse here of what the actual weighted sum of the labels or the label shapes in this case looks like. All right, and if we let it run for a while, things become better. So you can see the first label layer now has actually got some super threshold poses or some super threshold activation. So some labels actually have pierced the threshold. So we get a much better idea of what the shape of the object actually is. And you can already see that the shape estimate, or the shape that is the combined shape of the active labels, has become much more fitting towards the actual object, right? And sort of the rotation even has converged already. That's why this is actually already also nicely oriented. The shift is also already converging. Actually, it's not visible yet, but the first layer probably is. All right, if we let that run for a while, so now we have 3 possible labels active. All right, so the shift has now converged, right? It's gone above threshold here, but it already was quite nice before. Okay, and so if we let that run for a while, you will see that in the end, you can see that the third label actually is the one that wins, right? And now it actually matches quite perfectly. So it doesn't match so well up here, but that's because of the way we extract the shape of the object rather than of the estimate not being correct. Okay. All right, so we've talked about that. So this masking is, of course, kind of looks just like a bonus in this case because we don't have any cluttered backgrounds or anything. We haven't systematically evaluated it yet on cluttered backgrounds, but it also has some other nice uses. So for example, you can see here there are two objects in the input actually, and so I don't know how usual object recognition systems deal with that. But in our case, actually, we can then just focus on one of the objects, and the other one is completely disregarded because it's just multiplied away here. The same goes for if you actually have interaction with a human. If you, for example, recognize this tape dispenser, and then someone just grabs into this, because everything else here is kind of faded away, the hand actually isn't a large distractor in this case. Okay, minus 10 minutes, okay. So there are some applications, you've seen some of that already. Just a short summary, what we didn't really talk about was why object recognition is so difficult, but I hope you've gotten an idea of that. What I hope you really understood is how the system works, and please ask questions if not. We've seen some results, and we've seen why this matching is good, or why we can actually have this, this fading out of the input. Okay, so just 10 minutes over time. Any questions? Thanks for your attention first.